Welcome to day 5 of Docent training. We have a couple of things to address before we get to our main topic, which is climate change. And by the way, what a wonderful day to be talking about climate change, since climate/weather is foremost on our minds today. But I would like to introduce Emily Weedle. Yeah. Okay, Emily Weedle is another one of the graduate students. Would you like to say who you're working with and what you're working on?
Sure. So I'm being co-advised by Dr. Docent and Dave Hartnett, and I'm one of the woody encroachment people studying dogwood on the Prairie, so just some of the population dynamics.
Where are you from?
Hutch, yeah, from Hutch originally. And I'm a master's.
So she's taking the training virtually, and all of the videos are online so far. And Kelly, do you want to come up here? Or do you want to? Sorry. It's okay.
I'll fill your place, Steve.
Oh, yeah, please. While I was working on the videos this weekend, I spent a lot of time sitting at my kitchen counter, and these were sitting on my kitchen counter, and I started playing with them, as one is wont to do while you're sitting there. And it occurred to me that these are a perfect metaphor for the fossils on Konza, the Brachiopods versus the bivalves. And I think, and going through the video, it occurred to me that there may have been some confusion about the Brachiopods versus the bivalves, because I got to listen to that about 15 times. And the difference being that they're both hinged organisms that look very clam-like. Back 250 million years ago, the Brachiopods were very numerous. There was about 15,000 different species, as compared to a relatively fewer amount of bivalves. So if you see something that looks oyster or clam-like as a fossil in the limestone layers, you are most likely looking at a brachiopod. Currently, there's only about 300 species of brachiopods, and the bivalves have surpassed that. Brad, do you know how many species of bivalves there are? There's more than 300.
Shoot, yes.
Okay. So, but the difference being where the hinge is between the two shells, each one is a valve and they're hinged, as opposed to their body structures. And this particular, it's obviously a jewelry case, and it has a hinge, but if you open it, you see that there is a velvet flap on one side of the valve, and the other side does not have it. There's a definite top and a bottom that's hinged. That would be a brachiopod. And so once you're inside, you have the structure, the organism, and the two sides of the organism. The right side, if you were to split this in half, the right side would be equal to the left side. They are bilaterally symmetrical. So this is a really good example of a brachiopod. This is obviously a glasses case with a hinge. Flip it open, and the two sides are identical. You have a right side and you have a left side. You don't so much have a top and a bottom, but you have a right side and a left side with a hinge. This is a bivalve. Can you see the flap? If I do it like that, you can see that there's a flap. And because there's no flap on this side. If I were to hold these this way, would the two sides be identical?
No.
Would this side be the same as this side? No. You have a definite top and a definite bottom where the structure is. Brachiopod, bivalve. Does that make a little more sense?
It makes sense, but when you see it as a fossil,
Brachiopod.
okay,
That's going to be your default,
okay,
because there were far more numerous at that point in time.
okay.
They're also very small. And so the ones you're seeing, so the simplest thing would be to go to default, which is you're probably looking at a brachiopod.
So the other ones have the lines that go non-parallel around them?
The brachiopods are going to, and you kind of look at the hinge, and the lines are going to be perpendicular to the hinge. And I think that's what you're referring to. The lines are perpendicular to the hinge. But I would just go with the default of, if you see a little clam looking thing, do you agree?
Well, they're not always perpendicular.
They can be
Sometimes
fanned.
They fan out from a point of origin in the center.
Right. Okay. Okay, questions?
I've been on lots and lots of geology field trips with geologists that actually should know better. And they always say default. They don't say default. You just ask them, and they, oh, that's Brachiopods. Oh, that's Brachiopods. That's right. They won't even look. So in this stuff, you might as well.
And so that comes back to addressing what you need to know versus what kids need to know. Because very rarely are you going to be going into this kind of depth with a group that you're leading. If you're a paleontologist or a geologist, then you need to know certain things. If you are an environmental educator leading a general tour of sixth graders, if you were to go into that kind of detail, you would lose your audience. And so you need to edit what you say to them, because a lot of times it's detail that they don't need to know. If it's something that somebody asks, it's always nice to know it and to be able to answer it. It's always nice. But it's very rare that you're going to know every answer to every question that somebody asks you. So we try to skirt the line between we want you to know things, but we don't want you to expect that you have to know everything. But we want to enable you to know enough to answer the questions, and so you feel like an authority and you feel like you can answer those questions. But and this is, I think, something I said at the very beginning of the training, that there's no way that you're going to know everything. So the best that we do is try to give you as much information as we think that you're going to need to know, and to enable you with the majority of the information. Along the way, you learn things every day. Like I've said, I've already learned 2 things today. You learn things every day, and you learn what you don't know, which is just as important. And try to have reference materials available so you can look things up. And realize that there's absolutely no shame in saying, you know what, I'm not sure. We will look that up.
I think that's actually more powerful for the kids, to be real honest with you.
To show that you're human and that you don't know everything, and there's things to be learned. There's things to be learned, and it would be great if you went out and figured it out and they came back and told me. Okay? So today we are not going to be going outside unless you really want to. We're not going to be going outside. So we're going to be spending the day inside. Brad was nice enough to bring some mini Cinnies from the Lawrence Bakery. So we're not going to die.
Mini Sims.
But we've got a pretty interesting topic to talk about, and that is climate change. And climate change is one of the drivers for research here at Konza Prairie. So let's start with that word, drivers. Drivers are natural, for the most part, natural processes that shape the functioning of the ecosystem.
Jill, is there anything in our binders that we're listed
If you want just a blank piece of
That's
paper to
what
take
I'm-
notes,
yeah.
is that what we're needing?
That would be,
Yes, I
yeah.
was trying to take
Okay.
notes on the right page.
Sounds good.
Probably neon and ramps, but
Got this a little bit here. We can start with. We got 7 more pieces of paper.
Go ahead and get just a pile.
Yeah.
Just get a pile, because they're probably going to go through
Put 'em
this
in
one
the
page. Natural processes that shape the functioning of the ecosystem. For example, we talked about the three primary, and now we can use that word, three primary drivers that manage and maintain the prairie. What are those three drivers?
The value of animals.
Grazing.
Weather. Climate.
Okay, so we're going to get to that.
Yeah. And fire.
Grazing, climate, fire. And those form the foundation for research here at Konza. And climate, we'll back up. What type of climate does Konza have? What term describes the kind of climate that we have? Continental. And what does that mean?
In the middle of the continent.
Okay, so who said that?
Well, it turns out there was an interesting analysis this week in the web about how everybody claims to have the most unpredictable weather. And so they went through and analyzed that, and did that by taking a look at the average over the year, and then looking how far each day deviates from that average.
Right.
And I guarantee the continental part of the United States way kicked butt on everybody else. And in fact, you know, north of us, but we're still pretty good as far as how much we might deviate from the yearly average on any given day.
So the definition of a continental climate means that the location that you're referring to is in the center-ish of a continent, away from a large body of water. Because the closer one is to a large body of water, the less deviation you have from a norm. Because water is a buffer. It will absorb heat and it will release heat. It's a buffer. And so you're going to have relatively similar weather the closer you are, or steady, static weather the closer you are to a larger body of water. Case in point, you're never going to get the coldest location in the country for a certain day in San Francisco or in Seattle or in Boston. That's never going to be the coldest location in the country.
Or the hottest.
Pardon me?
Or the hottest.
Or the what?
Hottest.
Or the hottest. Thank you.
Hottest.
Right. You're never going to get the extremes where there's water. And the Great Lakes count for that as well.
You can get extremes on precipitation.
You're going to get extremes on precipitation, but not on temperature. Yeah. Because water is a buffer. So because we are far away from large bodies of water, and because we're in the center of a continent, it dictates our climate, and it dictates our vegetation. Because we have unpredictable precipitation, we have periods of wetness and then long periods of dryness, that dictates what kind of vegetation we have. So what is the dominant vegetation in the center of any continent? Grasses. Because grasses, this all goes back to the climate, because grasses have root systems that allow them to take advantage of that. Their roots are all, their fibrous roots all, for the most part, within the first foot of soil. And so this fibrous root system acts very much like a sponge and allows them to opportunistically absorb the water when the water shows up. And when you have long periods of dryness, the plants go into a quiescence, they go into a dormancy, but they're still alive. Now, would a tree be able to survive in those kind of conditions, typically?
Yeah, it depends.
It depends. It depends. But it goes back to the climate is dictating the vegetation, and the vegetation is adapted for life in that kind of climate. When you have changes like human habitation, like watering, like reservoirs, things become different from the norm. And that's when you get more trees.
Even in a natural landscape, you see more trees in areas where the water's focused, right?
For the water, at the bottom of the valley,
Bottom of the valley.
near a creek, near a water source. And that's where you would typically have trees. Trees aren't supposed to be found at the top of the hill in Prairie.
There's quite a bit of research also though that talks about the role of that other driver, fire, in the natural maintenance and creation of grasslands. So not only are we continental in our climate, we are also physiographically flat. And so if you take a look, I mean, the mountains are in a continental climate as well, right?
Yes, but they have trees.
And you take a look at the situation across Kansas, wherever there's deep, steep bluffs, there's always, you've got 400-year-old trees. So, the topography goes into that quite a bit. And so all those natural grasslands that you think about all around the world, they're in flat areas.
So why would, and that begs the question, why would trees not do well in flat areas? Why would trees do well in areas that are protected from wind?
Give us the answer.
And get blown over,
Well, you've got the physical,
dried out.
you've got physical blowing, trees could blow over, but you also have transpiration.
And you also have growing points, your meristem.
Getting damaged. But transpiration will play a big role in what we're talking about today, so let's go ahead and define that. Transpiration is the evaporation. Well, the movement of, but we'll start with evaporation of water from the surface of the leaves. And this is going to be affected by you tell me.
Wind.
Okay,
Temperature.
there it is. Oh, and let's give a third one. Wind, temperature. Come on, Emily. Humidity. Okay. So what conditions are going to increase the rate of transpiration, of the loss of water from a plant? Wind, high winds, okay, high wind. Temperature,
High.
humidity,
Oh.
do we ever have that here?
Yeah.
Okay. So you've got, and then what Brad was talking about, I don't know if I'm quite ready to go into apical meristem.
I know, I'm sorry.
Okay.
I don't think it's that complicated. So plants like trees have their growing point on top,
No, they have their growing points at the tips of their
the
branches.
tips of their branches, but on top,
Right, at the tips,
at the tips, and grasses have it at the bottom,
at the base of
Base
the
of the
plant.
down low to
Yeah.
the ground. So the growing points are at the tips of the
At the
branches.
tips, and they can become easily damaged.
Or the apex of the plant, so that's why it's called apical. So they have apical meristem, and grasses have basal meristem. So that's why you can chew it all the way to the ground, and the growing point's still alive because it's down here.
What's the term meristem?
Oh,
It's part of the plants where the cells reproduce and make more of it.
Basically
So
stem
it's-
cells.
Yes.
Can you spell that for me? I'm sorry, I just.
M-E-R-I.
Oh,
I'd never thought of the term stem cells in this context, but
Well, yeah, that's
really?
they're undifferentiated cells that can become anything.
Literally.
And so they're
Meristem.
literally stem cells. Yeah.
And we have an apical meristem, which is at the tip of the branches. Best example for this is if you have shrubs And you've probably done this before, where you had shrubs that got really leggy, and you wanted to fill in the spots. Have you ever done this before with a shrub? And what you do is you cut those meristems off, and all these little side branches come in. It
They
gets
all
thicker.
become meristemic then, so they're all.
Lilac.
Yeah, you know, you get the apical dominance.
So meristems grow
Down
out,
or out?
what, so I'm asking a question, I guess.
Yep, meristems grow out.
So like on
The
a
other
juniper, if
is-
you cut it back below the green, you never get regrowth on that branch.
So
Right.
for like a Christmas tree farmer protects the top of the Christmas tree, because if it were to break off,
Yeah.
you would have a flat-topped Christmas tree, and who wants to buy a flat-topped
Or
Christmas
a
tree?
branching
You
Christmas.
get a bunch of bushy
You
stuff.
get a bunch,
right, so
yeah.
water moves
And
cut.
that's called apical dominance.
And what's the other one? There's apical.
Okay, so
meristem.
you've got apical
Basil.
meristem.
Which is
Basil.
the roots.
Yeah,
Basil. Okay,
basil.
thank you.
She wasn't even planning on doing this, wow.
Well, it just,
Quiet.
when you said that, that made, oh,
Yeah,
because I was thinking, when all that grass is getting, I think
The
in
growing
terms of
point's
nuts,
down at the
this is good for me.
Intercalary. Intercalary /
Ooh.
basil. Uh-huh.
Intercal,
Yeah, you wanted to get into this. Meristem.
but anybody's played around with plants much has
Has run
seen
into
this and learned it without thinking about it.
Yeah, it matches your common sense or your experience working with plants.
Okay.
Of course, kids haven't done this.
Meristems can come in different flavors too, right? So you can get a floral meristem. It's when you've got tissue that gives rise to flowers. So when the plant decides it's time, it may form a different kind of meristem that gives you a flower.
Buds.
Buds, yeah.
All right, so transpiration. This is a major reason why we don't have trees in the prairie. And grasses are modified for life in the prairie. Prairie where that has a continental climate. Pulling it back in. Grasses are modified for life. Okay. So let's put down the characteristics of a continental climate. Because this will come up. And it is a good thing to reinforce this. Close to or away from water?
away.
Okay. And because of that, you have extremes in temperature. Extremes in temperature. Because of that, you have no buffering because there's no water. Okay, so extremes in temperature mean what? Could go both ways.
Hot and cold.
Okay, so it's going to be hot in the summer and cold in the winter. And we talked about this in the very beginning, that our average temperature is hardly ever reached. What is the average temperature?
In Kansas,
Average annual,
like 58 or something. When
Yep.
I read that.
average annual temperature at Konza. It was 55 degrees Fahrenheit. Whoops. We're also going to get extremes. In what other condition?
Wind.
Moisture.
Look at that third.
Moisture.
Okay, extremes in precipitation. And what are our two choices?
Drought and flood.
Drought and flood.
Hell and high water.
Pardon me?
He's said Helen.
Helen,
I-
Okay. And we're also gonna get wind. Okay, who wants to define wind?
So this is one of those things that your students, the younger ones, will come in with a misconception about what wind is because they created their own model of the world without testing it. So my model of wind when I was young was that the trees threw the air from one tree to the next.
That
Trees through air.
Through the trees
Trees
and the
through
flames
oh,
through
trees
the
through
wind.
the air like
Yeah.
baseball.
Yeah, and
Wow.
so they really don't understand that it's this difference in pressures between different places, right?
So is air pushing or being pulled? We'll start with that. Is air pushing or being pulled? Okay, so wind is air being sucked in somewhere. It's being pulled.
I know on the farm, we never looked at the current wind temperature, we looked at
I hate it when I
isobar.
do that.
Oh, that's
Right.
interesting.
Yeah.
The barometric pressure.
I just went back up.
But
to
you could
where I
ask a
started
question
that.
today, so where's the low pressure from where we are
Okay,
today?
thank you so much.
Okay, so if you look at a map, if you look at a weather map, what letter on the weather map is going to indicate the presence of windy conditions?
What letter?
What letter? A single letter on a meteorologist weather map. It's L.
L?
Okay. It is L.
Oh.
It is a low pressure system.
Okay.
If you see a great big L over eastern Kansas, what is that going to tell you? It's going to be super windy.
Hold on to your hat.
Okay, air's getting, and where is it going? Who's sucking that air in? Don't answer this, Brad. Go ahead, Forrest. Who's sucking that air in? Emily? The other letter.
Oh, hi.
Oh,
Okay,
right.
the
So
H.
It's providing,
The H. High pressure system.
I don't know if I'd say H is sucking it, I'd say the low is sucking it from the H.
The low is sucking it in from the H.
I mean, yeah.
It's going from low pressure to
So
high
it's
pressure.
magnetic.
High pressure pushing.
the air is coming from the high.
So,
To the low.
yeah, air's coming from the high.
From
to
the high to the low.
Right. So, I mean, you could call it a push, you could call it a suck. The deal is that the differential in the heating caused a low pressure, and this has to balance it out.
And the low, the air is going counterclockwise and up. That's how you get
Yeah.
tornadoes, so it's going up.
Counterclockwise up here.
Yeah. Right, in the southern hemisphere. Get complicated.
So where's the nice weather, with the L or the H? Yeah.
Yeah.
High pressure system's gonna be nice weather.
Temperature affects that too, right?
Yes,
And generally dry.
generally dry.
Bluebird skies,
Okay.
calm winds, under H's.
Okay. There's her. I knew there was something else I wanted to hit. Okay. So keeping all these conditions in mind, the plants that are here are adapted to this.
Joe, what's a simple opposite to continental climate? Marine? What's the word you said?
Maritime.
Maritime.
Maritime,
Yeah.
yeah.
You could say San Diego, Seattle,
Coastal.
San Francisco.
Coastal might be a, and a child would understand coastal. They may not understand other words.
Disneyland. Good word, too.
Going to the coast, going to South Padre. Did you do South Padre and Big Bend on the same trip?
Yes, but we go to North Padre.
We
Yeah.
stay where it's
North
cooler
Padre.
and less
Regardless, you went
populous.
you went to the Gulf Coast.
We did, we went to the Gulf Coast.
So you got to see the Gulf Coast versus the Rio Grande
Mountains,
Coast.
desert,
Yeah.
yeah. It was,
Where did you stay on
on North Padre. We stayed in a holiday.
I've stayed there multiple
Well done.
times.
This will be edited out. This is why we have the editing. Okay, so is weather and climate the same thing? So the climate that we were talking about, continental, with extremes, doesn't tell you anything about what's going out there right now, kind of, but pick any other day. Okay, it doesn't really tell you what the temperature is outside. It doesn't tell you what the precipitation is. It doesn't tell you what month you're in. That's the weather. The weather is the day-to-day temp, wind, precip. It is not the broad overall trends. So climate, broad, overall trends that dictate vegetation. We would not have prairie if we didn't have this climate. Which leads us back to climate change. Climate change being the change in the overall climate. Just saying it's a different way. Global warming is part of climate change, but not all of it. Oftentimes, people that you talk to will think they're equal. They're not. Global warming is part of climate change. So let's back up on that. And take a look. Two molecules. We're going to start with molecules. What is that? What is that?
Carbon dioxide.
Okay, so we start with that. Carbon dioxide. We don't assume that everybody knows that CO2 is the same thing as carbon dioxide. Kids aren't going to know that, so keep that in mind. You know it, you think everybody knows it. Kids may not know that. We will eventually get to this guy.
Methane.
Okay. We will eventually get to this guy. Right now, I'm going to get my red marker out. We're going to put one red star by CO2.
Put one more hydrogen on it.
Yeah, you need CH4. Sorry.
Oh, sorry. I was methylating.
Yes, you were.
That's right, it's a methyl group.
I was methylating.
Yeah.
Okay. 3 stars on that one. We'll come back to that. Forrest already knows where I'm, or not, yeah, Forrest already, you already know where I'm going? Bill?
Maybe go for it.
Maybe, we'll see.
We'll see where we're going with that.
I know some things about those molecules.
We're coming back to that. Okay, photosynthesis. The only natural process that takes in carbon dioxide. Only natural process that takes in carbon dioxide. Is that important? Yeah. Okay, so the very simple equation without any numbers, CO2, what is H2O?
Water.
Okay, water. And at the end of that, we get glucose plus some O2. We'll put some numbers here in a second.
What's CO2?
Well,
No,
I don't wanna
I
comment.
said, what's CO2?
oh, what?
I didn't say.
What?
What's oxygen?
Wait. What is O2?
O2.
Okay, well, you're getting ahead of me. You're
Well,
getting
you
ahead
had
of me.
defined all the others like water.
You're getting ahead of me.
Oh, I see.
All right, so what's O2?
Oxygen.
Oxygen. Okay. This process that takes in CO2 and water makes glucose. What's another simple name for glucose? Sugar.
I'm gonna know they said dextrose.
Thank you. And O2, which is oxygen. Okay. One thing I want to point out, a lot of times people will say that photosynthesis makes oxygen. Plants cannot make oxygen, no more than we can make gold. Okay, they're elements in a periodic table. You can't make them. Stars can make them. So what?
It extracts it or
Releases.
releases, okay.
Oxygen is released during photosynthesis.
Where's it released from?
Now you're
You're
getting.
getting ahead of me here, too. Oxygen is released from photosynthesis. Backing up, where did the oxygen originally come from? That dude right there. Okay. Water is the original source of our oxygen. Kids might like that.
You could, if you were presenting this to kids and you were actually playing with this, you could say, you'd have that oxygen over there. So where did it come from? Where could it come from? And they could do either one, and then you could describe
about
an experiment that would give you an idea of how England's experiment, for instance. And they'd figure out that it came from water, and that'd be really cool.
The oxygen and the CO2 is in the sugar.
What's that?
Yes.
Oxygen from the
Yes.
CO2 is in
Yes.
the sugar.
This oxygen is over here.
In the sugar.
Yes. So you get this because light hits the plant and breaks up the water molecule. You don't have to go into that. Okay, so then Brad's other question was, how does the plant get rid of the oxygen? You guys tell me. How does the plant get rid of the oxygen? How does the plant release the oxygen? Where? Yeah, okay. So we have pores in the leaves.
What's the matter with you?
Oh,
Guess what the pores are called? And actually, Greta knows this one because she looked it up. Okay, so the pores in the leaves, stomata is plural, stoma is singular. Okay. The pores in the leaves release the oxygen. We always write, when we write the letter O, the elemental symbol for oxygen, O is never by itself. O hooks up with another O, and we write it as O2. It's a diatomic element, diatomic molecule. Okay. Pores in the leaves release the oxygen, and you see this especially if you're looking at maybe a little aquatic plant, or if you're looking at some algae, and you can see little bubbles along the edge of it, and those little bubbles are, during the day, indicative of the fact that it is doing photosynthesis. So this is the process that takes in carbon dioxide.
So is a grass considered a leaf?
Yes, sir.
Okay.
Yes, sir.
So what's the chemical makeup of your glucose then?
Okay.
Where does the hydrogen?
Okay, so let's put in some numbers. Let's put in 6 molecules of carbon dioxide and 6 molecules of water. We're going to balance our equation, and we're going to get C6 H12O6 plus 6 molecules of oxygen. So balance your equation. We've got 6 carbons here to 6 carbons here. We have how many oxygens altogether? 12.
Plus,
Okay, plus another. Okay, so we have 18. So we have 6 plus 12, 18. Then we have 12 hydrogens. 12 hydrogens. We have our balanced equation. This is the foundation of life on Earth. It's the foundation of life. Do plants need to be able to breathe oxygen in order to do photosynthesis?
Did what?
No. In fact, photosynthesis happened before there was free oxygen in the atmosphere. There's free oxygen in the atmosphere because of photosynthesis,
But not in the plant.
but not in plants. Photosynthesis,
Yeah.
I'm not going to go into that.
I just.
Okay, photosynthesis has been around for 2.7 billion years ago. And Haley says, why? Right? Why? Sure. Okay. There were no plants around at that time. So who was doing photosynthesis? And where were the animals to breathe in all that wonderful air? There were no animals. 2.7 billion years ago, it was pigmented bacteria. You've been hearing about this from Milford Lake. It's your blue-green algae that was capable of doing photosynthesis. Blue-green algae. Yeah. And they were the first ones that did photosynthesis and started releasing oxygen into the environment. Oxygen in the environment at that time was toxic
Excellent.
because it's an oxygenator. It causes rust, for God's sakes. And that's how we know that it was there, because we started seeing rust. That's why we're seeing red soil, because it was rusty. There was oxygen there.
Korean red beds?
So let's flip this around. Make it a different color so it doesn't get lost. We're going to use red. Let's flip this around. Let's have glucose plus, we'll give it some oxygen, and we're going to break the glucose down in the presence of oxygen, and we're going to get out of that breakdown of glucose, we're going to get 6 carbon dioxides plus 6 molecules of water. It's the exact same equation, just with the arrow change. Do you guys see that? You are all doing this right now. You're not doing this one, sorry. But you're doing this one. Especially if you had some breakfast.
Many cities.
Especially if you ate a mini cine. This is aerobic, because you got some oxygen there. Cellular respiration. If you all take a nice deep breath and, hey, if you were to do this on a mirror, would you see some water mist on that mirror? If you did it to your plant, would your plant appreciate you breathing on it? This is how you talk to your plants. It's the exact opposite of photosynthesis. And this is one of our sources of this. When you have the breakdown of molecules like glucose, you release carbon dioxide. Now, if you have bigger molecules, bigger than glucose, you have some things that plants have made, if they have excess glucose, they store it. Plants don't usually store their excess sugar as fat like animals do. They store it starch and big long chains of hydrocarbons. And if they can get compressed underground,
Potatoes.
nice big long chains of hydrocarbons. And what do we call these, especially if you've got big puddles of hydrocarbons underground and solids under pressure? Call them fossil fuels. Fossil fuels are simply a whole bunch of carbon that plants have made and stored and millions of years ago, and they've gotten pressured. We dig them up, and what do we do with them? We burn them. We break them down, and we release carbon dioxide and water and some other things.
So the equation at the bottom, if you don't have glucose, but just have carbon-based stuff, is the same thing as burning things. So it's combustion.
It's combustion. You need to have
It's just slower in
oxygen,
in carbon.
and you need to have a carbon source.
We get it, yeah.
And the bigger your carbon, glucose is pretty small. The bigger your carbon molecule, you can have thousands of carbon molecules all hooked together in a nice energy source, and that's what I'm getting to is energy. The more carbon you have, the more energy you have. Well, bonds, the more energy you have.
But before you go on, one thing that's real important from a biology teacher standpoint is that a lot of people don't think that bottom equation is done in plants.
I had my hand up.
That's
because it said
huge. That's huge.
Plants
Okay.
need oxygen.
Plants need oxygen, especially in the cells that are not doing photosynthesis. What cells in plants do photosynthesis? Do the roots do photosynthesis? Are the roots green and exposed to the sun? It has to be the leaves. Are the plants doing photosynthesis other than the evergreens? Are the trees doing photosynthesis right now? Are they doing cellular respiration right now? You bet. You bet. Plants need oxygen. This is why you can kill a plant by drowning it. One of the reasons why. Yeah.
Jill, I would add the top process consumes energy and the bottom one releases energy.
It-
And so,
So,
what? Consumes energy. What, you don't like that? Why?
well, I think what he's talking about is a catabolic versus an anabolic
Okay.
reaction.
I was just getting into conservation of
But- Oh, right, so it's,
So I don't know that this is a process that is producing a molecule. This is an anabolic reaction you're making. Okay. This one where you're breaking it down is referred to as a catabolic. RXN for reaction. And it also releases, well, that's also going to be making some. For the purist. Okay. But I'm not going to get into that.
For our entry-level biology students, I find that it's helpful just to say, like, plants can make their own sugar using photosynthesis, that topically, right?
Yep.
They can't use that sugar until they break it down, just like we do in our bodies.
I think the energy that drives photosynthesis, it's important to note, is sunlight, right? So it's
Okay.
photons, it's eight.
Okay, so we've made, very simply, we've made sugar, then we've broken the sugar down, and we've seen where carbon dioxide can get put back into the atmosphere from the breakdown of the sugar. In order for this process to happen, you have to break that molecule of water apart. And this requires the sun's energy to do that, to break that up. It's going to release that oxygen. Oxygen's going to find another buddy and go off into the world by themselves. But the hydrogens stay. We're not going to go into the process of the hydrogens moving around. But this requires sunlight. Sun powers photosynthesis. And we're breaking, and it takes in carbon dioxide. Cellular respiration releases carbon dioxide. Okay. Moving on. We haven't yet addressed climate change. And we haven't yet addressed methane. Climate change this is the hard part, getting a nice clean definition. Okay. Okay. Change in Earth's climate due to a variety of activity related to human action. You're not going to get one single biologist who's going to disagree with that. Why? Take a look at that screen. This is the Earth's population. Anyone know what the Earth's population is right now?
Close to 7 billion.
We hit 7 billion and we're up and over.
It's been like 6 billion since 1950 increase, something like that. 1950 was a huge number.
If you want to get freaked out,
Okay, there we go.
City the size of Wichita every day. We have to find a space for it. Or maybe it's every hour, I can't remember last time I calculated. But if you go back to that graph, back in the early 2000s, I came into class in one day in October, and I told them this is the most important day in human history.
we hit 6 billion.
We hit the deflection point.
The curve began to bend.
The curve began to bend. It's the first time we saw the bend. We didn't know when that bend was going to happen. That bend gives us an opportunity to predict the maximum population.
I remember hearing when we hit 6 billion, we were going to be in trouble.
I think I heard Ken say we got it.
Okay, so let's take a look at that.
If
Why
you're as
that
old
is.
as Ken and I, you've been around since back before it was 3 billion.
Hey, I heard somebody ask this question one time, so how would you answer it? Of all the people who have ever lived, all the humans who have ever lived, what fraction of them are still alive today?
That's a lot of. I mean,
Most.
Most, yeah.
Most of them.
Most of the humans who have ever lived are still alive today. And I don't know what that fraction would be.
Okay. So why is
Isn't that
human,
mind-blowing?
sometimes you need to spell it out. Why is the human population a problem? Well, because humans need. We could just stop there. Because humans need. What do they need? Well, they need food.
And we're large organisms.
We're
not
large,
even
we're
small.
top level consumers. You know, if you like to eat beef, think of the amount of energy that goes into creating beef. Okay, so humans need food, and so we'll make a note here, top level consumer. It wouldn't be a problem if we were detritivores, that'd be a lot better. Eat dead stuff.
I just read an article one time that said if the rest of the world got half the amount of protein we eat in America, we need like 500 to 700 more meat. It's just unreal.
It's crazy.
Yeah.
Okay, so humans need food, and we're top level consumers, i.e., in other words, we'd like animal protein. It takes a lot of energy to make that steak. Oh my goodness. Humans need, well, and to grow this food, you need agriculture. And agriculture has to be more and more efficient. And to have agriculture, you're no longer going to have prairie. Humans need homes. To have a home, you're no longer going to have prairie. Humans need fuel for heating, for cooling, for mobility,
We're driving the Konza for once.
for driving Konza. We're all doing it. And this is one, humans need shopping. This isn't, this is, I'm serious. This is economic development. This is economic growth. Show me an economist who doesn't want things to grow. And we're not talking about the prairie.
The only one I know died in E.F. Shoemaker.
All economists
Yeah.
want growth. We can't sustain that. This is, Go
That's
ahead.
industry. That's like you said, that's industry that
That's
builds stuff.
industry.
Yeah.
That's industry, that's economic growth. Okay, if you got more people, you got more Walmarts. And you've got parking lots, and you've got the cars going to the parking lots, and you've got all the stuff going to the stores. None of that stuff is getting made on the prairie. All of these things are taking, except for like agriculture, but taking natural land away. They're taking natural land away and turning it into something else. Now, agriculture is doing photosynthesis, but doing the photosynthesis, during the growing season, and then it's bare ground. If you're taking those plants away, you're taking away these sources of photosynthesis for absorbing carbon dioxide. And you're taking fuel sources and breaking them down and releasing more and more carbon dioxide. So we're getting more and more carbon dioxide in the atmosphere. And I believe last year, was it last year that we hit? We hit
Over
400 parts per million.
Forever.
Forever. For a long time. For a long time, we were told that if we ever hit 400 parts per million, we're in trouble. up and over. This is gonna be one of those depressing topics.
Well, if you're gonna throw 400 up, you might wanna come up with, what a normal might be, how we might come up
Yeah,
with.
before the industrial revolution.
Which I'll bet you guys aren't correct.
I'm gonna have to,
400 parts per million.
It was higher in the past.
400 watts per million.
So that's like how many molecules are in?
Out of a million
Out
molecules,
of a million molecules, how many are carbon dioxide?
it's not very much of what you breathe. In fact, if it get up, in a room like this, it would get up to 800 to 1,000, and when it gets up to 800 and 1,000, you start getting really sleepy, and so you have to ventilate rooms, right?
Oh, okay.
Breathing gets more rapid. Have you ever breathed in and out of a paper bag, cold paper bag over your mouth?
You can actually cause yourself to faint.
Yeah, your breathing speeds up. You have to breathe rapidly, and you can fall over. You can make yourself pass out by
You
breathing
just
in a paper
do a
bag.
monologue plane, it'll be on there.
The number I remember is 180, and people were always saying if we double it, we're in trouble. Ken would say we're in trouble.
So this is the longest term of direct measurement of carbon dioxide that we have on the planet. And you can see it doesn't go that far back, but it goes back into the 50s when it started.
People have looked at gas bubbles trapped in ice in Antarctica or whatever.
Greenland, yeah.
Yeah, evergreen.
There it is.
It's interesting.
There it is.
Yeah.
Right, but as far as directly measuring, and see how it goes up and down?
that's a growing season.
So which one's spring and which one's fall?
Okay, so CO2 is gonna go down during the growing season, right? And CO2 is gonna go up during the non-growing season, during autumn and winter.
So the peak every year is right about now for northern hemisphere. So that's why it fluctuates.
And then the valleys that,
You can see it was down below around 300 in the 1960s, and I think probably around 250 around 1900.
Ice skating, you have higher periods of CO2.
Yeah.
It's the tornado.
It's the tornado drill.
okay. All right,
So how many, do they have an idea of how many trillions of tons of carbon we've released to the atmosphere in the last 200 years?
Yes, we do. And if you want to read that, you can look up the IPCC report. I can send it to you if you
Okay.
want. And
I saw that graph of the amount of people, I think it's 1960 or something, like 3 billion new people. Quite a few did.
in 1960, it was about 3 billion. Right.
Yeah.
wow. Let's see what last month. Okay, so why Mauna Loa? This is at the top of a volcano out in the Pacific Ocean. Why there?
Isolated?
Yeah, it's clean.
Mm-hmm.
It's clean.
If you did that here, it would fluctuate a lot more. In fact, you got some records. from
I was
there.
going to say, as a matter of fact, we have that here. We have monitoring stations out there, and that's one of the things that we're going to talk about today.
And if you go down into the grass itself when it's growing, or into a cornfield when it's growing, you won't hardly have any CO2.
Right.
It's all sucked into the plant.
Okay.
I just Googled it. During the ice ages, it was as low as 180. And pre-industrial, just like during the 18th century, it was around 270.
Okay.
So we're
So
in
it's
trouble.
kind of interesting.
Well,
That's the point.
it's always difficult to say what's in trouble, but yes, we're probably in trouble.
I don't know, I feel the same as I did 20 years ago,
Yeah.
50 years ago. So what's
But the ice caps are melting and the sea level's rising.
The people, it's definitely our offspring that are in trouble. We know. Okay.
It's great.
Okay, so the sun's energy. Sun's energy hits our atmosphere about, we'll get this in your notes so you can remember this. Okay, so we've laid the groundwork for the fact that human activity is releasing more carbon dioxide than the earth, than the plants or the vegetation of the earth can absorb. So the CO2 levels have gone up above 400 parts per million and are increasing. So let's make that note so you have this clearly in your notes. There's 400, actually, greater than 400 parts per million of CO2 in the Earth's atmosphere. And it is growing. And we've laid the groundwork of the fact that it's growing. If you want me to go back to the human population chart where it's going ching, 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 ching. Yeah, that's
Scary.
really disconcerting. Now, let me make a point here to talk about eco-terrorism. Be really careful about what you say to kids.
Yeah.
Oh, yeah.
Really careful, and just, we can just, this is more for your foundation, for your knowledge, not to really share with the kids because we don't want them terrified. But we do let them know that climate change is something that we measure here, and that we are looking to see how climate change affects the tall grass prairie. Okay. So greater than 400 parts per million CO2 in the Earth's atmosphere, and it is growing. What is it doing in the Earth's atmosphere? It, CO2, it is trapping the sun's energy. About 34% of the sun's energy is reflected off of our atmosphere. About 66% of the sun's energy reaches the ground and is used by the plants. Some of it is reflected back up and normally would be reflected out into space. The sun's energy, more of it, as the CO2 goes up, the sun's energy is increasingly getting trapped under our atmosphere. Now, if you were a politician, you would say, well, look outside. How can that possibly be? But we go back to the definition of climate versus weather. And to tell how the climate is changing, we look at long-term trends. We look at changes over long periods of time. And it's very difficult to make that argument that just because it's cold outside right now, that doesn't mean we haven't had the last 10 years, the 7 hottest years in Earth's history. And keep in mind, we were talking about the fact that we are supposed to be in our period of cooling in our Earth's rotation around the sun. We're supposed to be in a period of cooling. We should be in kind of a semi-ice age right now. But instead, we're having the hottest years on record. But apparently that message isn't getting across to certain politicians. So the sun's energy is increasingly getting trapped under our atmosphere. And we're seeing the ramifications of that. We're seeing, okay, so ramifications. We're seeing ice shelves breaking apart. We're seeing sea level rising. And here's the big one. We're seeing the permafrost melting. Where is the permafrost located?
I'll start with Alaska.
Yes, sir.
Russia and all
Yes,
across.
yes. Areas where you would have previously permanently frozen ground. And in that permanently frozen ground, you have a large amount of organisms that had previously been alive and were now dead. That's where you can find mammoths and all kinds of interesting things that were frozen into the permafrost. So the fact that the permafrost is melting is now leading, it's kind of like what happens if you were to leave your refrigerator unplugged, but you still have a bunch of food in there. It's a really great analogy for that. Somebody unplugged your freezer. What is happening to all your food in your freezer? It's rotting. What is rotting it? What kind of organisms are rotting your food? Wasn't rotting before, but now it is. Who's doing it?
Bacteria.
Okay. The bacteria is breaking down all of this food in the permafrost freezer.
And because it's underground, it's anaerobic.
Actually, well, what's that?
It's anaerobic, the absence of oxygen because it's underground and because it's bacteria.
But that's,
The-
yeah.
The waste product from this breaking down of the previously frozen materials is methane. Permafrost melting, releasing CH4, methane.
Yeah, that's the kid's explanation, but it's actually methane hydrates that were trapped 300 million years ago. And the amount of methane hydrates, like if I drove into Russia, we were looking at it, is 50 to 10,000 times more than the gas we've ever found in the world in conventional hydrocarbon reservoirs.
So it's like fossil methane.
So it's
yeah.
also releasing fossilized
And it's
methane.
what's causing
Well,
this.
you know, I would just say, anytime you have a creation of fossil fuels that migrate somewhere, what happened was, there was trillions and a massive amount, and it migrated but never got out of the ice in the permafrost, so it's trapped in there from the Permian and 300 million
Okay,
years
so
ago.
it's not just bacterial degradation,
No,
it's trapped
It's
methane.
trapped. We got,
Methane hydrate.
in fact, the U.S. government has test wells in Alaska trying to figure out how to recover it. But in Russia, we drilled through that, and there's like 500-700 feet of just methane gas trapped. You calculate the reserve, and it's beyond your comprehension how much methane there.
And it's also blowing up pieces of the permafrost right now.
Yeah.
And then you have a separate methane hydrate area that's just as bad, and that's the continental shelf areas.
Yeah, in Japan, everybody's trying to figure out how to make it work in terms of energy. The amount is
Okay, so
beyond your comprehension.
So why is this a problem?
Because as soon as it starts to melt, it releases the methane.
So why is methane a problem in the atmosphere? Okay, it's the stars. Goes back to our red stars. Carbon dioxide's ability to trap the sun's energy got 1 star. Methane's ability to trap the sun's energy got how many stars?
3.
Because it's 300 times more powerful at trapping the sun's energy than carbon dioxide. Methane is a real problem. Methane is a real problem. And so we have to address this. Or all of this is going to just compound and get worse. That's climate change. Go
There are
ahead.
lots of natural sources for methane too, and people like to use that as a false argument, for why we shouldn't be worrying so much about this. For example, when a cow belches, they belch out methane from
At the other end too.
and the other end.
I was
too.
going to say, who's going to say it?
But
Bill.
and then rice paddies, so tremendous acreages of the world are devoted to producing rice, and rice paddies produce a lot of methane. So it's coming from a lot of sources, but the scale, certainly from the permafrost, is orders of magnitude bigger. And then we've got methane being accelerated from other, human activities as well.
Landfills too.
So, pardon me?
Landfills,
Landfills.
especially all the food that we throw away,
Yeah,
that
a
all
lot.
breaks down into methane.
So, not that you should do this with kids because it'll get so scary, but one thing I think is that you should play with here is kids don't comprehend, people don't comprehend big numbers. And when you were just talking orders of magnitude, when a kid hears 3 orders of magnitude, they hear 3.
Doesn't mean anything.
They don't hear 10 times 10 times 10, right?
Yeah.
So you might want to work that in, might consider working that into your talks. They're trying to you know, develop this relative idea of quantities because kids don't do that well.
Yeah, yeah. Well, and like you said, you don't want to scare the kids. And so just say that climate change, but this, their visit here is one of science, and they may not be getting this elsewhere. And so they need to know that climate change is a serious topic that should be taken.
We've got a responsibility to educate them about this. It's their world. And so
Yeah, it
if
is.
anybody's gonna solve it, it's gonna be their.
But the
kids,
part that
their
most
kids.
of them are gonna be needing to get a good grasp of is the carbon cycle. If they get a good grasp of the carbon cycle, we'll be doing a good deal, and we can simply say out here that, you know, we're measuring that carbon cycle.
We are measuring that carbon cycle, and these are the
How much
tools that
things are
we're
going
using to
between
measure it.
each part.
And this is, and it's important.
I worked at the DuPont company for 17 years during the time we were figuring out what to do about ozone depletion. DuPont was on the firing line for that. Climate change is layered on top of that in so many different ways. So I, and along with a couple of other people, were trying to teach DuPont's chief technology officer this stuff. It's a bigger challenge than teaching these kids we're talking about.
It's really something, isn't it?
And very resistant. And,
It's like
don't tell me
politicians.
about CO2. Every time I breathe, I put CO2 out there.
It's like politicians. They don't want to hear it.
Very powerful people who know something good and useful, that's how they got to be where they are. But they're very resistant to, you know, things that don't match their immediate perception of the world.
And most of the argument from their side is going to the idea that, well, CO2 increase is gonna be good for us because
Yeah,
that's
that's
our
right.
plants growing.
Yeah, we're gonna get more plants, so it'll be healthy.
Not if you're cutting down all the plants to put in all the houses and the Walmarts.
And here's the other thing you run into constantly is people say, well, how do you know that? How do you know all this stuff, you know? And do I believe it? You know, there's a guy in Wichita I did date with this. Well, how do you know that? You know, they just don't believe it. So
Because there are scientists on both sides, so that's what you know, because I read the science on one side and science on the other
the
side.
truth is, they're not reputable scientists
Yeah, I
on the
was
other
going to
side.
argue with that. There are not scientists
The
on the other
numbers,
side.
and
Yeah.
so you
You
find
find
one or two.
contrarians. It's like, who's against vaccines, you know? You know, so I don't think any responsible physician or medical scientist believes there's a danger in vaccines. But you'll hear people say that. Oh, there's ideas on both sides.
Well, they'll talk
Yes,
about
right.
risk, but they won't talk about it being the kind of risk that the anti-vax people talk about.
That's right, there are legitimate risks to be discussed, but in any case, it really means something where the preponderance of evidence is, or
It's-
the best level of knowledge, where's the best knowledge?
I don't believe it's something to be believed. It's like,
That's right.
it's like the earth being round. Well,
Right.
there's people who don't believe the earth is round. Well, you're right. But the level of evidence is such that this is not.
But what you're
This is not-
referring to right now is the kind of thing you can do out here, and that is how we use evidence to make decisions. That's where our country's gotten away from in the last few years. I don't want to be political.
I would say trust too.
It
Trust
does
in
require
always having
trust,
trust.
but it requires, you've got to build trust that, you know, ultimately, our world has become too complicated with those 7 billion people in order to actually go by our gut. Our gut isn't, our emotional brain isn't capable of actually dealing in that level of complexity. So we have to base decisions on evidence the best we can. They won't all work, but we've got to convince kids that evidence is real important. And you can do that by helping them see things out there in the world that is real. And it's like I described the fossils in my classroom. Once they started handling fossils, they started realizing geologic time is interesting.
Jill, do you use that phrase greenhouse effect when you're talking about this with general audiences? We live in a greenhouse, and without that CO2 up there in the atmosphere and water vapor, we could not survive on this planet, right? So the greenhouse allows us to grow here in this greenhouse. The problem is, you know, the heat trapping effect, and that's a really good way to put it, I think. But the heat trapping effect is making this greenhouse intolerably hot.
So the answer is yes, you can use what terms you think might be able to communicate. And you've reminded me of one thing I wanted to talk about, and that was energy. Because this process is reflective of the fact that we've got greenhouse gases, and it's carbon dioxide and methane, increasingly building up in the atmosphere. What's it doing is increasing, and this is big, because this is climate change, is increasing the energy in the atmosphere.
Yeah.
That's what we're seeing. The increased energy in the atmosphere, okay, so we have increased heat equals increased transpiration equals increased moisture in the atmosphere, right? So now we've got
More powerful low pressure system.
We've got heat, which is a type of energy, and moisture in the atmosphere, and this is where we're getting catastrophic storms.
We've come full circle, we're back to talking about where does the wind come from?
These are the hurricanes, these are the floods, this is the catastrophic storms.
You want to talk about
This is all gonna be in the
the
video.
effect of your atmosphere
My
on
head is gonna
moderating our
explode
climate?
Makes your
I
voice
always, there's likely to be a kid on your team that has some clue about the weather temperature conditions on the moon. And the moon's just as far from the sun on average as we are, right? And every day it goes below the freezing point of carbon dioxide and goes above the boiling point of water on every single day on the moon's surface. So that gives you an idea what it would be like here without the.
Right, without the
Yeah.
buffering effect of the atmosphere.
Like, I guess that would, does that apply equally all around the globe? Or it seems like the catastrophic storms are more, I'm just gonna
Where you
like
have
hurricanes and the equator.
moisture.
Yeah.
Moisture and heat.
So there's
And
an
energy.
unequal,
Yeah.
there's an unequal distribution of
Yeah.
oceans between the northern and southern hemispheres, which creates something of an issue. But you don't hear about them, but there are massive thunderstorm and storm systems in the Pacific that we don't ever hear or see about because they don't hit land. They burn out over the ocean. You can look at satellite images of them and you'll take a look at them compared to a thunderstorm here that's scary to death. And you'll look at that and it'll be an order of magnitude bigger and you're wondering what would it be like to be there. So yeah, it's happening on the planet.
So what would that look like here then, when we're feeling the full effects of that in a continental climate?
I don't know.
Oh, you're,
Tornadoes.
Just-
wait a minute, are there climatologists? Even the climatologists can't tell us what's going to happen.
Yeah.
That's
Okay.
right. I worked with a guy who was fairly high in UNEP, in the United Nations Environmental Program. He said he didn't like using the word global warming back in the
Right.
late 80s. He said climate change. He
Climate
said,
change.
I can't tell you for sure what's going to happen when we double CO2 levels, but I can tell you this, you're not going to like it.
And that's a big problem.
Yeah.
That's where the trust comes in that Kathy was talking
Yeah.
about.
But there's not much we can do about it. We're past the point of no return, so our only choice is to adapt.
No, actually, it's not our only choice because we're still at another window where we can moderate. There could be a point of no return where there's not surviving for large organisms, to be real honest. But hopefully, we are still in a place where we can make some adaptations.
That question about a point of no return is like asking what's the most perfect prairie, or what's the most beautiful prairie. No return in what sense, So I think it's going to be very hard to reverse things from where we are, but we sure need to level it off unless we want it to get really, really bad. So
Which is why I pointed out that inflection point on human population. If before that deflection point, we didn't know if the ultimate population would be 10 billion, 15, or 50 billion. I will tell you right now that of the biomass captured on the planet, the estimate is that humans somehow grab 40% of it. So the biomass is that glucose side of the photosynthesis. of all the glucose produced on this planet, we're using about 40% somehow or another. Imagine if we were all of a sudden up to 50 billion. There's not enough energy coming into the planet for us.
That's, yeah, sustainability of the planet.
So the fact that we're on that deflection point means that we might time out, we might develop enough strategies, but obviously it requires everybody working towards a goal.
And that's where our elected officials can actually make a difference.
Yeah.
They can do something. They can do
Yeah,
something by working together as a globe.
Yeah.
We can make a
Because
difference by who we elect.
Because, you know, my friends over in China, China wants to be our standard of living. If they do that, then kiss this all their life, because they're gonna double the energy consumed in the world if they get our standard of living.
Well, what are you gonna do about Africa? Don't they deserve the same level
Exactly, that's what I
of
mean.
life we have?
Everybody wants our standard of living.
Why shouldn't they?
I know,
Yeah.
yeah,
But when I worked in
but
China
that
30
can't happen.
years ago,
It won't happen
talking
probably.
about one refrigerator per commune.
Yeah.
And if everybody had refrigerators there, now they're gonna, you know, the ozone, certain whatever it is, in Antarctica is gonna explode because
Yeah.
of the freon going out.
I mean,
I think they've taken care of that.
it's a tough problem.
They're actually working harder on climate change than we are.
They are. China's
Oh, yeah.
really, they want to be the world leader in environmental response.
And we want to be the world's.
China.
They're huge.
Of all
We
the-
just consume
All right.
and consume.
So-
Are we all depressed?
Because
Yeah.
they don't.
Yeah.
So, like, out of all of
Crazy.
this, like, it's very doomsday, right? But what is, like, main takeaways that would be trying to get the kids?
That's a
to
great
But-
question.
And it's kind of what Forrest was alluding to, and the main takeaway is that it is a serious issue that scientists are addressing, and it's something that we are measuring here, and we're doing long-term studies because climate change is affecting the prairie, and this is how we're measuring it. And so we then show them the tools that we're using to measure that.
Right.
May I
Do you
suggest also that what Forrest said was, you know, people are always saying, well, how do you know that? Well, you can make the point that this is how we get the information to know that things are changing.
Experiments.
We are actually measuring those changes right here.
And scientists are taught that opinion should be taken out of the equation, that you look at the data, and the data forms the decision and forms the direction that you go. And so that's another lesson to give to kids, is that this is not someone's opinion, this is what the data is telling us, it's data driven.
You
Do
had
you have-
99% of the scientists want this data. They want to believe, that, you know, they'd like to not have to listen to it either.
So do you ever see pushback with, like, some of the older kids who've, like, I mean, they're getting these ideas from their parents, right?
Yep,
So how do you typically respond to something like
You get a
that?
few flat earthers now and then.
flat earthers.
I mean, when you're talking
So-
to
so-
a group in front of their peers,
You address them, the parents and the kids alike, and say that this is a biological research station. We are looking at what the data tells us, and this is what the data is telling us.
I was just thinking about younger children, and I know we would never go that far, but just a trust issue part, again, if the scientists out here are using tools to get information, it's kind of like, you know, you don't, if you're not feeling so well, and your mom takes your temperature with the tool, a
That's a good idea.
thermometer,
That confirms that you're not
Yes.
feeling well.
yeah.
That's
that-
good.
That, yes.
So
you're-
making it
Uh-huh. Just that.
something
yeah.
relatable on their scale.
Your mother's trusting that you're not sick, you need to go to school because this tool told her so. Or the other way around, you need to go see the doctor.
Right.
And what about the point that this is why the prairie is important, and it's why plants are important, and that, you know, trees are important, and why we need as much as possible of.
And we kind of, with every visit of kids that come out here, we start with the fact that the tall grass prairie is important, because 96% of the original tall grass prairie is gone, and this is part of the 4% that's left. And so we're doing research on what's here that can tell us what's happening in our world. That, you know, a cornfield's not gonna really be able to tell us, but this prairie can tell us all kinds of things about what's happening in this world.
You know, the people that make connection to the land usually protect it a lot differently than the people that don't.
So we're better at that here in Kansas. I
Well,
came out
we
here.
learn that when we go on a tour with kids.
Yeah. I found myself thinking about this last week, and that is, what is research? And so this is a research station. What does that mean? And these days, I more and more hear the term research used to describe doing a Google search.
Yeah.
Oh, I did my research, right?
Right.
Is that research?
Looking at, hopefully they're looking at someone's
It's
research.
Look at somebody else's research.
Well,
Well,
that-
research is generating new knowledge.
Yeah.
Yeah.
New knowledge, answering questions that are still there, and generating new knowledge that nobody knows.
Which
And,
is, yeah, I think you made a really good point, because the elementary kids are gonna come in with the idea of research is what I did in the library.
Exactly, yeah.
That's a good, yeah.
You gotta do things in the library to get yourself ready to do research.
But you see, they're actually answering their own questions that they've never answered before.
That's
They
right.
don't know, they think that every question has an answer out there in a book.
Right.
Your research is different, because that
We're
answer is not
writing,
real.
we're writing the book.
We're writing the book.
Yeah, oh, that's what, yeah.
Yeah.
This is
We're writing
writing
the
the
book.
book out here. You heard that there's issues, well, we're writing the book to see.
We're writing the book to try to find answers
Mhm.
for these questions.
And it's based on scientific method and science, not somebody's opinion on it.
Boom.
Yeah.
I think they're using that term more and more, scientific method, with even the elementary kids.
Yeah.
these days.
So one of the things that's critical also is that, you know, that Mauna Loa deal started in the 60s. Without that critical data, we'd have a really hard time convincing people, right? So here we have a long-term monitoring site. That's what the LTERs are. They're monitoring the kind of changes that occur. And so without that, we don't know how much we've changed. You know, we all think we can do that pretty well, but any of us that are over 60 are already knowing what we don't remember. So, yeah, these long-term ecological research sites gives us an idea of the impact that humans are having on.
Very important.
And we're only one of them, there's lots more. That's-
There's 28 in total.
Good.
And they all started basically, it's the other thing to remember on climate change, is the entire country was behind acting on climate change going into the 90s. Literally, almost the entire country, over 80%, and that changed.
I'm thinking too about the, okay, how can I think, it's just that, if you start with the idea that this is a special place, you know, that's protected and there is ongoing information, but that information is shared with the rest of the world.
Yes.
And so that's why it's so important to leave the rocks,
Right,
don't pick the flowers.
Right. and when you say you're writing a new book, that, you know, you look at textbooks, old textbooks or history books, and you say, this is what we're gonna use in your class. Well, and it stops with Eisenhower's president. No.
Yeah.
You know, things change constantly, and science, you know. So this is an open textbook here. You're writing something that has no end. It's because it's gonna keep changing.
going.
It's gonna
Well,
keep
as a
changing.
textbook author,
Yeah, okay.
I can tell you that one of the most frustrating things in the world, because you know you're producing a snapshot, and you know that 90% of the kids and the teachers that are using it will treat it as if it's
Law.
correct,
It's
and it's
the
law,
end.
and it's not changing.
Yeah.
And my editors got really upset with me because I kept saying, well, this is an example of the ambiguity in how science operates, and we don't really know the answers. They got tired of that answer. So,
It's a book, so it needs to be black and white.
We
you're an
frustrate,
editor.
scientists frustrate people by saying there's uncertainty, but it's the margin of certainty that's key, and
And that's part of science too.
but you hit
that
it
level of
perfectly.
certainty is pretty high in
Yeah.
some areas. It's pretty good in some
The
areas.
only way we
and that's
can
certainly climate change.
actually cope with this is to be constantly adapting and changing, and we have a lot of momentum in society that's really going the wrong direction right now to do that. So we have, and you don't just tell people that you're wrong, you have to actually let them figure it out themselves. It's like working with a principal. You don't tell the principal they're wrong, you let them figure out something, you know,
Poor
let them think it's their idea.
That's an important
She's a
thing.
principal.
Well, I would say too, when you're talking to kids, like it's not just scientists that can contribute to that dialogue too.
Oh, absolutely.
Right.
Citizen science. is
Citizen
really-
science,
is
artists.
Yeah.
Actually,
absolutely,
we have to actually incorporate citizen science into any kind of solution today.
the humanities are really what it's all about, right? It's all about how do you live, how do you think, how do you feel. The art is what we're living for. in a lot of ways.
Right, if you don't have art, then what's the use of living?
What are you doing?
Well, Idaho's outlawed the use of climate change in their schools.
Oh, the word climate change?
They will not
The
teach
governor of
about
Florida wouldn't allow
climate change. Just passed that 2 weeks ago.
We're talking about the
Ignorance
importance.
is right all around us, all every place.
How do we adapt without accurate information? You know, if we're going to adapt,
Right.
it's a way to
That's-
respond to climate
that's-
change.
That's
Where
not
are we
reason.
headed?
And the
What
point
has
is-
happened? How
it's-
do you
it's like
adapt if you don't know?
What Bill said, you don't want to be right, but the ramifications of them not knowing this is just too huge. I wish I was wrong, but
I think, well, I know we can go on and on about this conversation, but I think the power of perception to change people's minds can be more powerful sometimes than information.
Oh, absolutely.
Yeah.
That
You
goes
can
back to the
present all the
trust.
data
That
in the
goes back to
world,
the
and that's
trust.
not going to change someone's mind if they think
Right,
they
right.
made it up.
There's actually a science of, you know, how you make decisions, how you commit to belief and stuff like that. And it's not, and just like the climate change data, it's not promising.
When I was in law school, I signed up for environmental law, and I went to the first day of class, and the professor said, you know, what should environmental law be based on? And I said it should be based on science, and he said, no, it shouldn't. It should be based on what people in the community think it should be. And so I dropped the class, and I went back when there was another professor teaching it, and we just taught the law, and took it then. But
I took environmental law.
That kind of stuff is very complicated, you know, so I've heard people say that the mission of science is to put good information in front of decision makers who are elected. They're not, you know, scientists aren't making those decisions. And so how the decision gets made, how it gets weighed. So I don't know. I've banged my head against that wall for a long time, you know.
I can tell
Thinking
you,
all you have to do is tell people the right information and good things will happen.
right,
It's not
I can
true.
tell you my own anecdote about this, and then we'll take a break. No, I need a break, sorry. Go ahead, we'll take a break here.
Let's just call it
Go
like that.
ahead.
I'm in that same
Watch
thing.
out for the plunger. So, you know, my parents, like I said, I'm first generation college. My parents are not, you know, they read one newspaper, and that's the local newspaper, and they watch the local news. And so climate change is something that some wonky people in Washington were talking about. But power of perception, they're seeing that, you know, and they're in Sioux Falls, they're seeing that the winters are not the same. The river rarely freezes completely anymore, where, you know, we used to go down there and ice skate on the river, and, you know, it was a lot colder. And so they're perceiving, and my mom said, that's global warming. And I wasn't gonna say, no, that's climate change. No, but I was like,
She's
yep,
on her way.
she's on her way.
But half the people I meet up there are like that warmer winter.
And there you go.
They do, because winters have been really tough. But they're seeing there's a discernible difference, and now they're thinking there's something going on. Yep, but think of how many 70 and 80-year-olds there are compared to, you know, there's both.
How many people have been hearing in the last week that it's been colder in Europe than at the North Pole? It's
They
really
set brand new records at the North Pole, above freezing.
Above freezing, yeah.
Yeah, and so it's been colder in Europe than at the North Pole. So what does that say about climate change?
Yeah.
People are freezing. We had such intense cold here, right? And they'll say, oh, I don't believe this climate change stuff. You ever see it so cold? But it's warmer at the North Pole. I think it was actually warmer at the North Pole, literally at the North Pole, than it was here in Kansas when we were having some of that intense cold too.
Well,
There have been,
not only that, but the entire west half of our country was setting record highs.
yeah, at the same
At the
time.
same time we were hitting these lows.
And some of those cold days, people were saying, look how it's so intensely cold here. You know, we're, I don't know, setting some cold records maybe locally. But on a very day when those kinds of facts were being reported, the Earth as a whole was experiencing its warmest day on record in the history of weather data keeping. You know, but they can calculate an average temperature for the entire globe, you know, at any given moment. So anyhow, those are things that bounce around in my brain and keep me up at night. You're talking about feeling scared. I don't know.
The other thing you might want to deal with on the Konza is, so one of the NSF grants that I got, I kind of bragged about it in the paper, and it was I was co-I on a Monarch Watch grant. I had no concept what was about to happen, but one of the local English teachers wrote a scathing letter to our local newspaper about the waste of government funds.
Small compared
It was, so you have this rationale to have to deal with. There's a lot of money spent out here in the context of people's lives, right? And, you know, there's pieces of equipment out there that cost more than what people make during an entire year. And you're wondering how do you justify that? It took a great deal of restraint on my part, I guess. I wrote a letter back and told her, I said, yeah, it is a lot of money, and that's why we're so happy about it, because this lets us do such and such and such and such, which included hiring 3 people for 3 years. I said, have you thought about what it costs to hire 3 people for 3 years? And suddenly there goes 50% of our grant, right? It's gone already. And I said, and we justified that based on how many kids we are going to have affected by this process, which was in the tens of thousands. Turned out it was in the hundreds of thousands. So, you know, got the money back for it, but most people's budgeting doesn't think that way. They don't work that way. So you might consider that, just in case you get one of those flat earthers you got that are saying, I can't believe you're wasting all this money out here.
If you ever get a chance to go to NCAR out of Boulder, I was part of when we were building the supercomputer, which is in Wyoming, because they didn't have the power in Colorado. It has 43,000 cores in it. It maps the entire world's weather in real time. And they have a globe about as big as this room, which is I don't know how they do it, but it's in the air. And you can see the entire world's weather at that exact moment. And people
online.
Yeah.
I don't know if it is online.
I think
It's pretty cool though.
Yes.
Yeah, the GCN used to be every section, and I think they got it down to every quarter now or something like that on the super.
Well,
Like I say, section, you need 1 mile by 1 mile grid.
Straight up.
Yeah, on the
Yeah.
surface.
I think we need to take a break.
Too excited.
And then we'll come back and we'll look at some of these tools, and I'll see if I can find that online. So it's 10:50, let's take a 10-minute break and come back at 11 o'clock. Part of today's discussion, and we will be talking about the
Starting a new page.
equipment used on Konza Prairie to help us measure both the weather and the climate and other chemicals in the environment. And so if you would kindly refer to your binders, there's going to be 2 different handouts that we're going to be looking at. The first handout is called Research Around Headquarters. It is under the purple tab. It is right smack dab in the middle of all of those documents in the purple tab, but it is going to be the thickest document. Right smack dab in the middle. So if you find, and it's got a bunch of pictures on it. Research Around Headquarters. If you would pull that out, please.
Oh, it's right up your drawing map.
That's it?
Which I don't have that either.
Yeah, we'll be,
We're using different years.
yeah, we're back in the old days.
Surely I have. No.
So behind the purple tab Right for
Maps. Huh. Mine was missing, but she just gave me those.
Was missing it? Thank you for, thank you. Are we all
Now you're missing it.
no good? Okay. So this document is basically a fact sheet for the equipment that can be pointed out to tour groups that is within an easy walking trail of the headquarters area. And so each of these different pieces of equipment is highlighted by a bullet there on the first page. But there is one bullet that we need to remove because the equipment has, since this was produced, the equipment's been removed. And that is right in the very middle, we have the sun photometer. The sun photometer that was placed by NASA is no longer there.
Does that mean the sun's not shining?
The sun is still shining, and the sun's radiation power is still being measured, but it is not being measured by that equipment. It is now being measured by the neon towers. So it's still being perceived and recorded, but it's being perceived and recorded by the neon towers. That piece of equipment had outlived its usefulness, and it was breaking down frequently, and so they just cut the ties and removed it. As you can see, a lot of the pieces of equipment are referred to by acronyms. They love the acronyms. So take a look, there's everything spelled out there. There's a definition for climate there for you, if you're looking for that. Forrest and I were chatting, no, it was Bill and I were chatting about the fact that I do have the beginnings of a climate change fact sheet, and it's just fermenting off in my computer. But it's something I need to put together so you can have a concrete piece of material to refer back to.
So would that be like talking points then too?
Talking
Jill, that we would
points.
use?
That would help to distill it down.
Yeah.
It's just a very difficult topic to distill sometimes.
Right,
And so that's
especially for younger children.
What did they say?
That's what I'm trying to do, so I might lasso Bill into helping me, or Brad into helping me, and Bill.
Neon.
Yeah,
I don't
I'd love that.
Yeah,
I'm just-
yeah, because it's like I said, it's fermenting, pardon the pun, but it's working.
This is just,
Okay.
okay.
So what this document consists of is photos and diagrams of the actual equipment, but it doesn't really give you an idea of where that equipment is located, and you guys don't want to go outside today. I'd take you out there, but listening, you wouldn't be able to hear me. But I do have a YouTube video. It's a two-part video of John Blair, who's one of our principal investigators, actually giving a presentation on this. And so I thought I would just go ahead and show that to you, if you were all amenable to that. Yeah? You're like, whatever, just do what you're gonna do. Okay, but the thing is, he knows the equipment quite well, and he can...
Is it listed in the videos list?
Is it listed in the videos list?
On the website?
Yeah.
Okay.
Yeah, this is on the Konza Prairie channel.
Okay.
So if you wanted to watch it again, and again, and again, you certainly could. And he's going to talk about the NASA sun photometer, so just realize that it's no longer there. Is that open? No. And we're going to go ahead and turn the light. Dang, we're good.
That wasn't even here.
I'd rather read mine over there.
So's principals, he did it all the time.
That's right.
All
I've
right.
seen teachers do that to get the room quiet.
Okay, I don't know why that's cutting off the screen. I don't know why that's cutting off the screen.
There's no way to drag it.
Doesn't-
Whoa.
I think you need to go to display.
For no momentito. Yeah, the VGA was causing some problems. And this will also give me a chance to show you how to find this. So just going to YouTube, you can tell I watch a lot of, apparently Lily Tomlin and Jane Fonda.
So is my wife.
They're hilarious. They're
That
hilarious.
is funny. I kind of lost track of, what is it called, their names?
Grace and Frankie.
Right, Frankie, yeah, Grace and
Okay, so it's funny if you haven't seen it. Okay, Konza Prairie Channel. There it is, just look for the bison. And I think, Retta, were you looking at something down here?
I'm sorry?
You were the one, you were looking at, who was looking at the birds?
It was on the
Was it on the
Keep
computer?
webpage, on the Keep page. There was a PowerPoint presentation.
Oh, yeah, that is mine, that is mine.
Yeah.
I will
thought
take credit
it
for
was.
that.
It was really good.
Thank you. So you're seeing that the training is available there. You'll see yourselves. It's the best thing in the world to sit there and look at yourself and edit.
Is that like Googling yourself?
It's awful. Okay, so you can see all the videos that are available. Okay, back in the old days, YouTube gave us a limit of 15 minutes for the videos, and so I had to break them down into smaller pieces.
Oh boy, that took it.
Yeah, then they changed it, thankfully, but I wasn't gonna go back and redo.
Yeah.
Let me see if we can hear him. Try to hear him. Still can't hear them. Okay. Now we can hear him.
So Jill's an expert to take a visit pictures of weather-related, climate-related stuff that birds are taking that new radio waves and doing that. So I'm just quickly running through some of these. So, when you see these out in the prairie, these are for collecting rainfall, but they're not for rainfall amounts. I'll show you the metal rain gauges we use for rainfall amount are very
Can you guys hear me?
precise, but
Kind
they're
of.
terrible for chemical analysis because the rain reacts with the metal. So to collect samples for chemical analysis, you want to use plastic, inert plastic.
Plastic rain
And that's what
gauge.
these are.
Chemical
So it's
analysis
just,
of the rain, not really caring about the amount.
In a crushed plastic jar, and that collects samples we can analyze for the chemical concentrations. So that's what it is.
Okay, so how about the big eye balloon?
Oh yeah, big eye balloons. So normally a lot of times out here there will be the big eye balloons, and that turns out, go ahead. Scare the birds, well, yeah, exactly, because what we don't necessarily want to measure is the chemical concentration of bird. That's not going to end up in the funnels. It doesn't work, does it scare the water? I don't know. I think it does help. I know I was afraid of birds. Yes. The other thing I'll tell you is that there's a lot of people gathering around ponds, and some cases, so the other thing that happens is bugs or a bit of a leaf will fall in there. Something like that happens, we have to toss the sample because it's contaminated. We want clean
They don't want the birds pooping in the water. So they scare the birds
These things
off.
are only empty after it rains. They're left out there, and then when we get more than a 3 millimeter rainfall, that's when we do like those. And they're taken back to campus so they can be analyzed for the chemical content. And there's lots of pictures of these floating around, so just put up clothes.
I was being complete.
This actually is a rain gauge. It's just to supplement the other rain gauges we have. So you can measure rain depth in here. And then this is the acid wash bottle and the funnel that we use for collecting rainfall. See, but this doesn't have, it doesn't have a fine edge. It's not designed for quantity. It's just a and this was the edge. They're all labeled to their different locations around campus. About how many? About how many? I want to say 8. I will say 8, but I don't know if that's exactly. I think roughly matches the number of metal rain gauges we have scattered around, which is also nice. that's important because even a small place the size of Konza, rainfall varies across the site. From the south end to the north end, you can get different rainfall amounts. Originally, the reason we have multiple rain gauges, it was set up so that you could triangulate across those if you wanted to, and estimate an actual rainfall amount across the whole site. So a lot of our other climate and weather-related equipment is all located here in the headquarters area. And this is our original weather station that we set up at LTR and we operate independently.
There's a lot more pictures of all that.
Yeah, so let's see, let's zip down. So within our weather station, we have these,
I'm just curious about how often or what percentage of the time your water samples get contaminated with, is it quite often an occurrence?
It is. I don't know, I would guess maybe a quarter of them get contaminated. And not as much with bird droppings, I don't think have that stuff up, but just insects dropping in there and things like that. Yeah, so that's always the problem with these samples. You need to collect a lot of them. These are rain gauges we use for a map. And you'll see these as you drive around Konza because there's some scattered along the main road as well. And these are lane rain gauges. They're made by Belfort. It's the company Belfort Lane Rain Gauges. The basic idea is that they have a very precise opening of a known area. It's got a sharp knife edge on the top. So you know exactly what area it's collecting from. The rain goes in here and collects in a bucket inside there that's sitting on basically little pan mountains. And if you open this door, there's a chart recorder in there with chart paper that's slowly running on a little clock mechanism, and there's a pen that's tracing against it. So when it rains, it pushes down on that, and the pen will trace.
It's weighing, it's a scale. And then there's a paper drive, and it's recording how much is.
And read from there what the rainfall events have been. These are calibrated about once a year. The next one is looking down into the Belfort rain gauge.
Belfort rain gauge, and it's in your paper.
This is a newer kind of rain gauge. So the Belfort rain gauges are mechanical. They have to be calibrated annually. And they're just subject to more error than we would like sometimes. So a newer kind of rain gauge, this is a vibrating wire rain gauge. It also works by weighing the rain. It uses a different principle. It's got 3 strain wires that measure the amount of strain depending on the weight of rain. And I don't know the physics behind this. It's a vibrating wire method though. The frequency with which the wires vibrate is directly proportional to the weight that's being pushed against the amount of strain on it. So these are thought to be a lot more accurate and they don't require as often.
More accurate. This is vibration of wires.
The truck backs are one of these. You're not happy. But so this is but we're supplementing our other rain gauges with this one right now at the headquarters area. That's the only place we have a vibrating wire. And see, if you collect bugs in there, that's not part of it. And this one we don't empty regularly, so these things have probably been collecting for a while. We would use this for chemical concentrations, just for amounts. It's a great picture. If you go in the headquarters area, we have 2 of the old Belfort rain gauges, the metal can rain gauges, and one of them is over here without this fence around it. And this one has a little kind of fence with baffles around it. This was originally set up because in Kansas, a lot of our rain comes in sideways, right? We need these doors, and the wind's really blowing. And the question was, if the wind is blowing really hard, is how much of that rain is just skipping the top of the bucket? Is it not going in? And so the thought was that if you put up a wind baffle around one of these gauges, we'll compare that with a gauge that doesn't have a wind baffle and see if there's any difference. And it turns out there's not. They've left this up, so we have two rain gauges that are kind of redundant with one another.
Did you guys hear all that?
What I didn't catch exactly was it turns out that.
They're the same.
They're the same.
So he said that
Didn't make
there's
a
not.
difference.
There's no difference, and so that's why there's plastic over the top, and there still is. It's probably the same plastic. It's like 3 years ago.
Really doesn't seem to have much of an effect.
That'd be some good data to share with classes.
Yeah.
Yeah.
It'd be good data to share with classes and also for statistics classes.
All of this data is online.
Rise. So there are some rain gauges we don't use in the winter because they don't work well for snow and ice. And so they're covered with plastic and duct tape, and very soon those will come off in the winter. the vibrating wire is the ones you we have a lot of other agencies that set up other monitoring equipment.
CastNet. So look up CastNet.
This is actually operated by the EPA. It's part of a network called CastNet.
Clean Air Standards.
CastNet. It's Clean Air Standards in Transit. And what they measured ozone, but not stratospheric ozone. Stratospheric ozone is the good ozone, it blocks ultraviolet radiation. Ozone in the troposphere is generally considered bad. It's a strong oxidizer, it's part of smog in cities, but it occurs naturally as well. And the EPA is curious about monitoring spatial patterns of ozone over the country.
Okay, used to collect ozone. They've now disabled that. And that was disabled a couple of years ago because the EPA was using that for regulatory purposes. And the Kansas Department of Environment and Health, I don't know what the name of it, Kansas Environment and Health, I don't know what it is, I'd have to look up what their official name. Objected to that, and so did the Nature Conservancy. Didn't want the equipment here to be used for regulatory purposes. And so we are no longer measuring the lower level ozone. We are now measuring sulfuric oxides and nitrous oxides, the acid rain components from the burning of fossil fuels.
So the ozone regulatory issue, wasn't that associated with the burning?
Right, and so it was being affected by our local burning, and they didn't want our local burning to be part of the regulatory decision.
So neon doesn't collect that?
Neon probably does. Neon probably does.
They probably just
But it's not going to be used for regulatory purposes.
Burning area that should be relatively clean, relatively unaffected, at least by urban activity. And so they monitor tropospheric ozone, is one thing they do. And they also collect aerosols, particles in the atmosphere that contain nitrogen and sulfur. They do that underneath that upside down bucket. There's an inlet that takes gas vacuum in the trailer to an ozone monitor. And there's another inlet that has a three-stage filter pack that collects particles, collects aerosols. And that's useful information for us, because the aerosols that contain nitrogen and sulfur are parts of our nitrogen and sulfur budget. We'd like to know how much is coming in annually from aerosols.
So it's kind of cool. There's this plastic hose attached to these filters, and the plastic hose is basically a vacuum. So it's sucking in air, and any of the particulates that are in the air are getting caught in the filter paper. And so the technicians come every Tuesday morning and lower the boom, so it gets lowered, and they take the filter paper out. Additionally, red-tailed hawks love that pot. And they will perch on top of that pot, and so when they bring the pot down, you can see blood all over the top of the pot.
So bringing their prey up there, or?
Well, they bring their prey back up there and eat it.
Yeah. So, but they're still doing this, it's just not, they're not giving the information for regulatory.
They used to do ozone, sulfuric oxides, and nitrous oxides. They're not doing ozone anymore. So sulfur and nitrogen oxides.
Okay, that's what I wrote down, okay.
So John?
Yeah.
So they share their information with us?
They do. So the deal with them is that we provide the technical support, so we change out the filters, monitor the station once a week. We recalibrate the flow meters. Rosemary, one of our technicians, does that. And I think we also pay the electric and phone bills to operate this. They provide all the equipment, they do all the chemical analyses, and they maintain the data that they provide to us. So we have partnerships with EPA on this one.
The filters are in the structure, so that's just part. There's no one up there in the top.
The filter pad's actually up under that bucket. And so this tower, Rosemary climbs this every Tuesday. She does. It's hinged and it's on pulleys. And so when she does it, she lowers this every week. And then you pull out. It's pretty cool. It's really heavy. You have to wear a hard hat when you do this because you don't want to fall and you're in trouble. It's a stainless steel case container that has these three-stage filter packs, and they're treated differently. So one collects nitric acid vapor, one collects sulfur dioxide aerosols, and the other one collects ammonia-containing particles. And then those all get sent back to, and there's a whole network of these, I think there's roughly 100 and some test bed sites around the country, and they're all analyzed in the same way, same protocol.
So did you get that? There's about 100 other sites that are doing the same thing.
Associated with this, there's a lot of micro climate measurements. So wind direction, an anemometer, which measures wind speed. So those are the little cups that spin depending on wind speed. So that's an anemometer. This device is called a pyrometer, P-Y-R-A-nometer. It measures solar energy. Okay, so it measures the total amount of solar energy coming in. Lightning rod, yes, lightning rod as well. This is our weather tripod. So this is the one that we set up back in 1980 or 81 to start measuring weather on Konza. So it's got the same storage bin, actually, just look at the top of it. This is for measuring air temperature, and I believe air temperature and relative humidity, if I remember right. This is just a separate antenna that sends the data back to campus. We used to have a data logger that recorded data, and then somebody would manually come out here and dump it once a week or once every other week. Now most of our devices at headquarters are all wireless, and they send the data directly back to campus. So on top of the hiking trail hill, there's a repeater that sends data back to an antenna on top of Bushnell Acker Hall, which then is wired to send data back to Bushnell Hall where we live. So the data loggers still collect data here, but they send it directly back.
Is that data published anywhere on the site? Like
It's on the LTER site. You can see what the temperature and
Yes.
wind speed is of Konza immediately.
Awesome.
Yep.
LTR.
And I'll show you that after we do this.
What else do we have? We have a tipping rain gauge, which again, this one's winterized for now. It's another kind of rain gauge that works. It's got a bucket on a teeter totter that tips back and forth. So one side of the little teeter totter fills up and dumps, and the number of dumps back and forth tells you the amount of rain. It's called a tipping bucket rain gauge. So we have a lot of rain gauges. But it's like a man with multiple watches. You never know what time it is. You never know how much rain. Take averages. This is for rainfall chemistry. And so this is again part of another network. This is the national, I'll give you the abbreviation first, NADP.
NADP, National Atmospheric Deposition Program.
NADP network out of line with 5. And you can see all the data as well. That's the National Atmospheric Deposition Program. It was set up in the 1980s to address acid rain primarily. To look at the rainfall chemistry, and especially acid rain as a problem in the northeastern United States. There are 220 or so sites though scattered throughout the
220
US
sites. I think that's in your, should be in there.
basis. And it's useful not only for looking at pollution, but for ecosystems ecologists, I want to know how much nitrogen and phosphorus is coming into the rain. And this is the way to measure that. So there's two buckets. There's a dry bucket and a wet bucket. And there's a sensor. There's probably other pictures here too, right? Yep. So there's a sensor right here. When it rains, so today we went out here. When it rains, it shorts out a little switch in this sensor. Closes the switch. It causes this lid to move over the dry fall bucket and to expose the wet fall bucket. So while it's raining, this bucket is collecting rain, but it's clean rain. There's no bugs or birds or anything. And then when it stops raining, there's a little heating element here that dries it back out fairly quickly, so the lid goes back and covers up the wet fall bucket again. It keeps that rainfall sample clean, so it's only wet fall.
Okay, so this is activated by rain. I used to have a docent who would go out there with groups and he would spit on that. He would spit on that to activate the tray. But it screwed up the data. So he got yelled at.
Don't do that.
Yeah, don't do that.
What is collected in the dry fall bucket?
Dust.
Dust.
And they do. They take a look to see what chemicals are here to the side of the dust.
So once that moves over then, it's open to the elements?
Yeah, because it's ostensibly raining.
Okay.
So rainfall has triggered this tray to move over onto this one, and that collects the rain, and then the rain is evaluated for
I
chemical
had it backwards in my head.
chemical content.
Okay, got it.
But then does it close automatically when the rain stops then?
Yeah, that's what he was saying, that there's a little a heating element that drives this, and then when it's completely dry, the circuit
I
reconnects.
got it, I had it backwards.
It's another way of collecting rainfall. The dry fall bucket used to be used for collecting dust. We really don't use it for
Used to
collecting
be.
anything anymore because it has
Okay,
one
he just
contamination associated.
said what I said was wrong. So, used to be
There's
that.
other ways of getting dry fall estimates. So that's part of the national network, measuring the chemistry of the rainfall.
Do you sense remotely somewhere the number of times they are?
He's the spitter.
So,
Myron. Myron was the spitter.
No, I don't think it's remotely sense. That's a really good question because there is a data logger that tells you, because if I go out there and lick my finger and stick it on there, which I have done on occasion,
John's responsible.
Yeah. Yeah.
She knows.
I think it's gonna be that. He's just admitting it.
That's enough.
You see what I have to deal with?
So you cut out the next scene where he's getting after him, huh?
Yeah, right.
And so every site has the exact same instruments calibrated.
Okay, so this is, I skipped out of the beginning of this. This is the Noaa weather station, National Oceanic and Atmospheric Administration. And that's kind of a fun one to show to kids because it's like space age, just big out there. And that big gray cone at the top really brings a lot of attention in. So it's National Oceanic and Atmospheric Administration. They use weather stations, and I think there's 114. Can you guys see it on your sheet?
It's under, is it under the US Climate Reference Network?
Say what?
That's under F, US Climate Reference
F.
Network.
Okay. Oh, that's right, CRN, Climate and Reference Network. Thank you. CRN.
This is 114.
114.
But it's actually NOAA now, you said?
It's operated by Noaa.
Okay.
Operates the Climate Reference Network. Yeah. And it's a really cool piece of equipment.
The national standards in the exact same way. They have built-in redundancy, and this is meant to be a high-quality climate reference network. So what they have here is we have redundant air temperature sensors and relative humidity sensors under these little.
Okay, so redundant, meaning repeated. And so these three with the hoods are all doing the same thing. They're taking the air temperature. And the hoods are protecting the thermometers from the sun's heat. So they're trying to get as true of an air temperature as they can.
I thought that said a third one's relative humidity.
Well, those three are all three temperature, and there is relative humidity on there too.
The reason that they have shelters is you don't want to put a thermometer in direct sunlight, right? That's going to influence what you're interested in measuring is air temperature. So you put them in these little shelters and you aspirate air through there. So you're actually measuring air temperature, not microclimate under a shelter. So we have air temperature, relative humidity, there's wind speed and wind direction.
And the relative humidity, it looked like he was pointing at, it's like back behind here. There's a bar extending off there.
There's a pyranometer, again, for solar radiation. And it's a data logger to collect all the data. There's also soil temperature and soil moisture curves associated with this. What's unique about this, it's different, is that little gray cone. Do you know what that is? As well, but you know what's under the cone? It's a satellite transmitter. So when you see those gray cones scattered around, because there are a couple of other instruments, that is sending data directly to a satellite network. And so that's the way NOAA gets their data transferred.
It doesn't go through much now.
It does not go through much now. But again, we worked with NOAA on this. We have direct access to the weather station. We can download the data directly. Patrick can check it to calibrate against our station. So there's a lot of advantages to working with these partner organizations. So this one says again, the data goes directly back to a national database. And you can find this online. If you look at NOAA, Climate Reference Network, there'll be a map of sites. You can find the Konza site, and you can even get there and see.
We'll take a look at that here after this is
It's
done.
totally publicly accessible.
We'll see what the wind speed is.
And again, there's the satellite. This is, again, just a little lightning rod essentially. Anemometer for wind speed. There's showing the housing for the temperature and relative humidity sensors.
I'm curious on the anemometer. That's a mechanical device. I know they have temperature sensing devices that do not depend on something mechanical. Why are they still using the old stuff?
Yeah, for weather stations, I don't know. The mechanical anemometers are considered to be, I think, standard for weather stations. The other kind of anemometer I'm familiar with, the kind of use of a flux tower. Those look like a series of 3 fingers pointing up and down, and they're called sonic anemometers. And the way they work is they actually produce sound waves. And based on, I think, Doppler shifts in the frequency of those waves, you can determine on a very fine scale and very short time frame wind speed and direction. You need that for flux towers because you need to be able to measure like a 10 hertz scale, the differences in wind movement. For these, all you really need is one broad brush measurement of wind direction and wind speed. Short answer is I don't know. I guess it would be more expensive and it's more data than hygrometer. Is that what I'm talking about? Periodically, those need to be cleaned off too, so because dust and dirt settling on them is going to influence things. Oh, and we also have a rain gauge associated with this. This is inside the fence. So when you see the big fence, this is a snow fence. And again, the idea is this is a standardized station. So even in the desert, they have the rain gauges surrounded by a snow fence. It's not going to snow there. But they have the exact same sort of setup at all the sites to standardize it. So double ring snow fence. And there's the rain gauge protected inside there. And again, the baffle system, there's also a vibrating wire rain gauge, just like the one I showed you before. The baffle system is designed to break up with it.
So what's cool is they've got the standardized format for all 114 of the stations. And they've got these in Death Valley and they've got these in Hawaii with the snow fences.
Cute. So how do they protect all this equipment when they burn headquarters?
They have people that put water around it.
Okay.
Yeah.
Well, and it's actually burned right up to them. I mean, they do burn.
They get it. Yeah, but they're real careful about it. Lots of pictures. Oh, there's the sun photometer.
This is another device that satellite transmits data. In this case, the data is transmitted. It's a NASA site, and Patrick should know this. I know. I can't remember which site it's actually transmitted to. The device is actually over here. This is just the transmitter. This is a sun photometer.
Okay, so let's save some time because I think that's the last one. And let's go to the Climate Reference Network. So if you can remember, Noaa, and that says CRN. Doesn't have to be capitalized. I did that just so you can see the letters a little more clearly. Okay, so from here, you want to see what the weather is. So look for the eye. Look for the green eye. See the latest observations. So it's organized by state. Do we want to go through all the states? Not today. And there we are.
There's one out in Oakland.
Yep. So up here, you can pick the day. Pick the day. We're looking at 11 o'clock. There's our temperature. Going down. We have it in Fahrenheit, we have it in Celsius.
Evidently missed those snowflakes.
Yeah, I got the same this morning.
I saw them this morning.
I had to.
Last time we had just like 9 minutes.
How about wind? Should we take a look? Okay, so let me back up and tell you how I did this. Okay, sensor data. And then here's our choices.
Cool.
Going to wind. And this is times 1.5 meter per second. We can change
Meter per
We
second.
can change,
It says meters per second.
right there,
Yeah.
we can change the units. Nope, that's
Think it-
temperature, precipitation.
What's that little symbol between the years?
Right there?
Yeah, what is it?
It's a clock.
Not letting me.
Okay.
Thought I could change it.
I don't know what meters per second means.
Yeah.
Oh, thank
Maybe,
goodness, I-
maybe below it.
There's the other.
There you go, 1.5.
You'll have to update it.
This is your fault, Ken.
What'd I do?
Actually, it's Steve Jobs' fault. He got in a fight with the Java people, or the Flash people.
Well, that's right.
Well, he wasn't taking it.
All right, this is gonna take
I
tomorrow.
like this flashes the rest.
Are you saying you're trying to change it like to miles per hour?
Yeah.
Yeah.
I'll just look up and convert.
Thank you, Evelyn.
Is 1.5 like 1.5 meters above the ground level?
See what the weather channel says.
That might be,
That would be my guess. And so it's measuring wind speed 1.5 meters above.
I think you're right.
So what's our meters per second?
Let's go to the fastest one. Oh, type in second average. That's interesting. Let's do 13.53.
Meters per second. That's 30 miles an
30?
Oh, but the weather channel says 18, so
Oh,
that's
what do they
way
know?
off.
What do they know?
18. Of course, this is out here.
One spot.
Yeah,
one
this is
spot.
right
Yeah.
here. One spot at one
It
time.
feels like it. That's what I was saying to Dawn when I got here. I said, it feels like that. Or
Here's our
stronger
solar
than
radiation.
24.
Oh, where's that?
That's what it was earlier.
Hold that over there.
Can you go back?
So can you change that then to a monthly average or a weekly average? That be?
Yeah, I'm going to the month summary.
Day to day.
Oh, yeah.
But it's probably just gonna be for the last 6 days. I can change it. But you can, so here's the data, and you can manipulate it. Let's go to, what's the site? Aha.
I thought you were gonna take us to the future for a minute.
I was excited. We're all anticipating, oh, we're going to 2000.
A little wrinkle in time.
It's thinking.
Did you hit go?
Yes, I did. Do you see the bar?
Can you ask questions?
That's my fault. The bar is definitely my fault.
Did you do the bar?
I couldn't get you faster speed out.
That is your fault. Okay, so here's our data. Aha! Ha ha ha, I knew I could change it somewhere. There it is. There it is. So looking at the historical data, you can put it into, this is last April. Looking at our wind, looking at our rain. We had 5.1 inches last year. Let's go to 2016.
You know, if you remember last April, we had a whole bunch of really high southerly winds.
Did we?
And the monarchs got blown all the way from Oklahoma up here in one day.
That's what I, you know, remember that
One
picture?
day. Oh my gosh.
We were looking at the really
Yeah.
pale orange monarchs.
And I happened to be at Canopolis doing a hike up there and saw, I can't remember now, I've got it recorded, somewhere around 8 to 10, maybe in the teens. I even saw mating pairs.
It was crazy,
Which
Mona.
is, you know, typically in April, you see it about the second week, first week if it's a good year, but you only see 1 or 2. I mean, this was unbelievable.
Well, and we didn't have any food for them.
Yeah.
The milkweed, they came up too early because milkweed wasn't sprouted.
Yeah, we
But
had them, our milkweeds were about that tall.
But you're not worried about food for the adults, you're worried about where they're gonna lay their eggs.
Yeah,
And so, all they have to have is a bud in the ground,
we had that.
and they can lay their eggs on
We
that.
had that.
Aphids get a ride like that too, which is a problem for crops.
Yeah.
Blown up here in droves.
Yeah.
That must be, that must not have.
What
It
about,
says
so,
it was 16.
Yeah, but the rain is wrong.
Oh, yeah, it still hasn't,
Jill, at the bottom of that table, I noticed there was data about extremes, so it shows what an extreme is.
Mm-hmm, yep.
So can you ask a question like, what were the strongest winds recorded on Konza Prairie last year?
I don't think I have that algorithm. I mean, I'm sure they have the data and
You
they
can
can do
extract
it.
it somehow, but it's not just
We'd
easy.
have to wade through
It's
it.
not easily presented.
Bringing this up. We've got some rain. This is when we flooded. After these, this is,
Oh, yeah.
and I'm gonna put it into US customary for inches. There it is, right there.
Wow.
This is when we flooded. This is what, that was the rain that took out the Nature Trail Bridge. Because it already rained.
You already had plenty of rain.
We already had plenty of rain. We were saturated after the 24th, after our 1 3/4, 2/4, and it, yeah, that 3-inch rain took out the bridge. So this is fun.
Uh-huh.
You can find all kinds of
Is,
stuff.
I didn't see, is there a point where you could download it, the data, or?
Copy paste might work.
I would think if you played around up here a little bit, you could probably
Yeah,
find
Maybe
it.
under resources.
Reports,
Oh.
data.
Probably, that's
So
not-
play with that, reports, maybe get something. Monthly summaries, maybe here.
yeah,
Lots of data. Okay. If you wanted to see what's happening, actually, I'm just gonna go here. I can figure out how to type. I go to our flash page. Synthesis, it's not, let me try it again. There it is, go to that one. We call this the flash page, and you can see this is the page for the station, this is us, then there's the LTER. That picture's still loading. Go ahead and click on the LTER. There's your weather. 37.2 degrees Fahrenheit, wind 20 kilometers per hour, so I guess we're switching.
So can we translate that to English?
Emily,
So what?
That's
I don't always have
Kilometers
That's
per
about
hour
30.
Oh, yeah, it's gotta be about 30. Is that what's?
we're just
I'll
gonna
check
agree.
it. I'm gonna check it.
She's going.
No, a kilometer is 1.6 miles per hour.
So 0.62.
So if you want to read more about the core LTER research, there you go. That's not very much.
Looks like you got volcanoes there on that.
Right, it does, doesn't it?
That's a good full center.
Fumaroles.
Growing history of related projects, data. So this is where the data is. Lots of stuff you can find on here if you want to play around with it. Okay. Any questions?
My head's exploding
I'm
today.
sorry.
No,
I'm
don't be
sorry.
sorry at all. It's wonderful though.
Lots of good stuff. So here you can just scroll through them all.
Tell me where this goes.
20 kilometers per hour is 12.
12.
And a half miles
We know
per
it's
hour.
faster than that.
That's what they're saying.
I think it's
You could look at the data per watershed. How much fun is that?
Oh my
Find a favorite
gosh.
watershed.
Off the top of your head, do you know which watershed gets the most rain on average?
Not a clue.
Probably is not all that much variation, but there may be consistent.
I don't know. You get to ask Patrick that question tomorrow. Do you guys have your red schedules out? What is tomorrow fire?
Tomorrow's fire.
Okay, so you can ask Patrick that question tomorrow. He is the burn crew chief, and he also used to be the primary technician for the LTER, and he'll be able to answer that one. Which watershed has the most rain?
How many watersheds are there on the Prairie?
There's about 50. Yes, 50 watersheds.
That and the majority of them flow into the King Creek, or not necessarily?
I can show you the map that shows the Kings Creek.
The
Majority of them, yes. Will empty into the Kings Creek watershed. Did I give you an old schedule?
She must have printed hers off.
But I knew that we changed things up a little bit, so, no.
Yeah, don't look at the white one, look at the red one.
Yeah, I'm not sure right
I
now.
would just throw that away.
Okay.
Well, yeah, King Creek, John Creek.
And tomorrow,
It's nested.
if the weather is amenable, we will go out and take a look not only at the equipment, okay, so you'll get to see all of the different
Thank you for not
equipment.
taking us out to equipment today.
You're
Yeah,
welcome.
that was